Hello again. Once again, we're talking about another video involving Lewis structures. So we have this problem. We're going to be covering Lewis structures, molecular geometry, and the concept of polarity in the particular problem that we're talking about here. So in part A, we are talking about drawing a Lewis structure of ClF3 and stating its molecular geometry. So again, Cl is in the middle, and you have fluorines on the sides, like so. Let's determine the number of valence shell electrons. Chlorine has 7. We have one of them. 7 times 1 is 7. Fluorine, again, group 7 of the periodic table when we have 3 of those. 7 times 3 is 21. 21 and 7, 28 total valence electrons. So now we've got to distribute the valence electrons in some way, shape, or manner so as to satisfy as many rules as possible as far as structures are concerned. First things first, the molecule doesn't fall apart, so you need a bond here, you need a bond here, and you need a bond here. 2, 4, 6 electrons, 3 bonds, 6 electrons. 28 minus 6, 22. Got 22 left over. Now we have to satisfy the octet rule around the terminal oxygens. So we have 2, 4, 6, 2, 4, 6, 2, 4, 6. 6 times 3 is 18. Leaves us with 4 left over. The 4 have to go onto the central atom. 2 here and 2 here. Okay? Minus 4, 0. So what we have here is an expanded octet around the central atom. We have 5 pairs of electrons around the central atom being chlorine. So when you have 5 pairs of electrons around the central atom, the electron pair geometry is trigonal bipyramidal. As far as the molecular geometry is concerned, the pairs of electrons that we have put onto chlorine have to go on the planar part of the molecule. If you can imagine this being a triangle like so, and you have an axis going along this way, it's a trigonal bipyramidal structure. The 2 pairs of electrons have to go around here because they occupy the greatest amount of space. They want to be as far apart from each other as possible. Here you have a 120-degree angle between these two. So that's how we can manage that. So when we're talking about the molecular geometry, pretend that you can't see the small little electrons, the pairs of electrons around the central atom. The molecular geometry we have left, draw a line here. Draw a line here, is T-shaped. So since it's T-shaped, now we've determined the geometry of the compound. As soon as you have a lopsided molecule like this, the determination of whether it's polar or non-polar, it can't possibly be symmetrical. So therefore, you already know that it is nonpolar. Justify your conclusion based on molecular geometry using the bond dipole arrows in your explanation. Let me draw the molecule again. Cl, F, F, F. Pairs of electrons here, pairs of electrons here. So now we see that we have the positive atom is in the middle, the electronegative atom is on the outside. So therefore we have a dipole this way, and we have a dipole this way. These two cancel each other out. They're the same strength because you have the same atoms on either side. However, this one right here does not cancel out with these pairs of electrons. You have a greater electron density over here. So the actual dipole is negative going in the downward direction. So the overall dipole points down in this case. These two cancel, this one doesn't. So therefore, this is a polar molecule. Okay. And that's your Lewis structure.